Yeah, Ari, that's perfect. We're gonna be going over just the complete basics. What we've been into what Ethereum is, what the blockchain is, just going over the basics. Okay. I think we'll just get started right now. Okay, so yes, thank you everyone for RSVPing. My name is Rajan. We'll be doing a custom blockchain workshop. So consider this a deep exploration into the next generation of what the internet is and what the internet can be. You've probably heard of things like Ethereum or Bitcoin, just the idea of a blockchain in general. And it is a very confusing concept. I understand. It took me a very, very long time to understand it myself. But I hope that this can sort of explain the fundamentals and what you really need in order to create your own. Because when you make something, that's like the truest form of understanding. We've learned that as hackers and in Hack Club. And I think that's the best way to approach this, especially with the Vitalik AMA and a lot of things I guess pertains to this new era of a digital world. So a little introduction. Hey guys, I'm Rajan. I like to call myself your friendly neighborhood activist. I am a 16-year-old based here in Toronto, Ontario, in Canada. I'm currently working on 2 startups. One I've been working on for about 2 to 3 months with a few people. It's a patient health data decentralization application or platform. It's something we've been working on for a while. The second one I started about 2 weeks ago. It's more about digital neighborhoods and how those can sort of bring exclusivity to those. And I think that's something I'm working on, and it's a really cool idea, but it's pretty recent. I really like The Weeknd and Kanye West. I love music, and I've been working on web interfaces, platforms. I've been coding for about 1.5 to 2 years. You can find me at Rajan Was Taken on Twitter, GitHub, and Instagram, because Rajan is a very common name. It's taken almost everywhere. So yeah, you can find me there, and I'd be down to chat about anything, or just if you want to reach out about any questions. Yeah, that's perfect. So let's get into what we're going to be doing today. We're going to be building our own blockchain in about 100 lines of code, and we're going to focus on 4 main things after we talk about what blockchain is. We're going to talk about proof of work, which is ensuring the validity of a transaction. We're going to talk about encryption, so we have whatever data and encrypting that so that it's for security. We're going to talk about something called asymmetric ciphering. This is by far my favorite, where users can encrypt and decrypt information. And finally, chain validity. This is how we prevent hacking, and we can actually ensure that the chain is valid. So what the heck is blockchain? In about the late 1990s to early 2000s, the era of exploration began. This is when the idea of Web 1 was introduced. And in this era of Web 1, things like Google or searching arrived, and people can now explore the internet. There were websites for almost every business. There was Google to search things up. It was an era where anyone could now scavenge the internet and get any information they needed. Then in the mid-2000s to late 2000s, the era of exploration began. This is where platforms like Facebook, Twitter, all these sorts of platforms came together to create an era of creation, where people can now, rather than scavenging for information, create it themselves. This is where the whole idea of social media came about, and where these explorers now became creators. The only problem was this was very centralized. And so now in the early 2020s, this is where the idea of decentralization came in. And the whole idea of Web 3.0, where rather than having data in a private database or private storage unit in Facebook headquarters, it was now distributed and owned by its users. And this is sort of the next generation of privacy and what the internet can truly become. So in blockchain, there are 3 main things: decentralized data, immutability, and distribution. In decentralization, this is where we have a network-based connection in between people. Rather than having data stored in one place, it is stored virtually everywhere. Then the next thing is immutability. Rather than having things that can just be posted and taken off, items on the chain are permanent. And how do we ensure the validity of something? Well, this is where the idea of letting the blockchain know whether to accept it or not. But once it's accepted, it's there forever. And we'll get into validity later. I'll explain it all in depth. Finally, distribution. So all participants have a copy of this public ledger. And this truly ties to the idea of when we're tackling public power distribution versus indulgence. And when we're talking about power distribution, rather than having data in one place, it's given to everyone. Everyone now has some power. You may have heard of something called a DAO, or a decentralized autonomous organization. In this case, it is the people that have the voting power. And they use things like blockchain in order to verify this and ensure that the people making these decisions are is bringing safety to this whole method. And that's really important when it comes to what blockchain is and what it can mean for whether it means small communities or highly scaled communities. So in terms of the Vitalik AMA that happened 2 days ago, I absolutely loved that myself. And in terms of blockchain, there were 4 key things that I took away from this. The first thing was blockchain is a public ledger that aims to build decentralized applications. Things like Ethereum are built so you can build things on top of it. And you use that blockchain to create applications that are decentralized, that are stored on the blockchain using things like smart contracts, for example. A smart contract is just a method of transaction. Rather than having to send it, for example, to a database and fetch that back, you can use a smart contract to connect and interact with the blockchain. The second thing is a block in the chain contains transactions. And every time a new transaction occurs on the blockchain, a record is added to every participant's ledger. What this means is the blockchain exists with transactions. So whether you are signing into something or whether you're actually sending money in actual transaction, it's all stored and it's all immutable and it's all on the chain. The third thing that I took away from the AMA was that blockchain security measures and public ledger make it a prime technology. There are so many applications, there's so many use cases such as social media networks or just NFT collections that make it very modern. And this is why it's being used, because we know it's secure and we know it's scalable. Finally, assets are distributed instead of copied or transferred. Rather than having things just taken from one place and then stored in another place, it's actually just distributed across all the users. And this is the idea of decentralization. In a business, for example, if the company is decentralized, power for decision making is given to the employees. In the same sense, in the same sense of that analogy, in this case, power and decision making is given to the users on the blockchain. So if you're still confused like what a blockchain actually is, this is a nice graphic that I found. So consider each individual thing as a block, and there are a certain amount of blocks. This block, for example, is 1,337 on the blockchain. It's at that position on the chain. It has individual nonce. This nonce is a single-use identifier for the user and for the block's data. It has the actual transaction data. It has the timestamps, and it has its hash. Hashing is a way to turn whatever information you want into a fixed length of just random characters. So A5E17826D right here, that represents all of this data. And so rather than having to store all of this, you just store a simple hash. And then on the next one, you say, okay, this one has its own individual data, but the previous one was this, so I know this is next, and it has its own individual hash. And that happens for the next one. It has its, it represents a previous hash as like the actual data, and then the current hash. And this is very useful in terms of, okay, so how do we verify what happened before? How do we verify what's happening right now? And this is the epitome of the blockchain, ensuring validity while also cryptographically encrypting the data for each individual block with its single-use identifier, which we call a nonce. So this is sort of the process of the blockchain. It looks a little confusing at first, but it's pretty straightforward. So you have your transaction. So your transaction is it's a smart contract. It's a signature. It's an actual transaction where you're sending money. A transaction is just what we call actions on the blockchain. This is then mined. When you mine it, you're sort of turning this into a hash, and you're using your single use identifier to figure out exactly where that is. Once that's mined, it's encrypted. This is where things, for example, as asymmetric ciphering is used, where you have individual people encrypting and decrypting the information. Then we use sequential order, and by sequencing this goes, like, if you go back to the graphic, they go one by one as a chain. So this is 1 3 3 7, 1 3 3 8, 1 3 3 9, and this is sort of the idea of sequential order. And then finally, this is all sent to a transparent distributed ledger that all users have access to. So I know that was a lot at once, but essentially the idea is it exists through transactions, and then you can encrypt these transactions. These are then put on a blockchain and then verified whether it's valid or not. If it's not valid, which I'll get into later, then we can say it's not feasible, and therefore it doesn't apply. On the blockchain, rather than preventing hacks, you can just see, okay, is this valid or not? And if it's not valid, then you just completely wipe it away and it doesn't matter anymore. So the whole idea of preventing hacking isn't really through, okay, we have these advanced measures and this advanced security. It's just, is this the right place on the blockchain? And if it is, it's valid. If it's not, then, oh well, it doesn't work anymore. So let's get into some code right now. So hopefully everyone can open up a replit. So I'm going to need anyone that wants to actually code this to go to something called replit.com. It's a shareable and collaborative IDE, and you're going to want to go, and you're going to want to click plus here. On the plus, you want to go here and you want to click Node.js, because we're going to be using JavaScript. Oh, thank you, Belle. I'll also share what I'm working on in case you want to see what I'm coding live. And you can title anything. I'm going to say Hack Club, let's say Blockchain Workshop. And once you're done, you create the REPL, and it should take you to a page like this. I'll just give you guys a couple seconds to work on that, and I will create a join link. I'm going to kindly ask that you don't erase any code, or you don't change any code that I write on there, just for ethical reasons, of course. But yeah, if you want to see what I'm coding live, this is the perfect way to do that. So yeah. You should be able to see what I just wrote live, and if not, you just look at my screen, and then you can work on this on your own REPL. Move this out of the way. So the first thing that I spoke about in depth was the idea of hashing. So hashing is when you take the transaction information and you turn that into a fixed length. And we're going to use something called SHA-256. SHA-256 is an open source library that we can use in order to take in the information. Oh, yeah, for sure. I'll zoom in, my bad. Font size. This. Hopefully, is that big enough? If not, I can zoom in more. Let's see. I'll just zoom in there, 110%. Perfect. All right, so we're going to be using something called SHA-256. This is an open source library that you can use in order to turn any data into a hash. For example, if you take a look at the graphic here, you can have your individual keys, any data you want, you put it into the hash function, and it outputs for every index an individual hash. Information like this, it just goes on and on for a certain length. And with that data, that becomes an individual indicator for the key. And so we are going to be implementing that first. So I think I got 1 second, folks. Yeah, just make sure you have the replica's open. Just making sure people have access. All right, perfect. So the first thing we want to do is actually install SHA-256. So we're going to go down here to the shell, and you're going to write npm I crypto.js. Add this in the chat. So you're going to want to type that into your shell. And once it's done, you click enter, and it'll do some stuff. And once that's done, you should end up with two files: a package lock.json and a package.json. You do not want to touch these files. You just want to leave these, and we'll access that later. So the first thing that we want to do is create a class. So class hash, and we're going to use something called constructor props. And this is a method to initialize an object state and class. So we're going to say constructor, and we're going to call 4 different things. We want an index, so this is its position. We want the timestamp, we want the data, and we want the previous. Once this is done, it should look like that. Now we want to actually give these things values. So we're going to say, so we're reading something called props. So this dot props, this dot index equals index. This dot time equals time. This dot data equals data, and this dot prev equals prev. This is the very beginning. Now, this is just indicating, okay, this is the position, this is the time, this is the actual data, for example, the quantity, and this is the previous hash. But how do we actually encrypt the data? How do we actually make hash? So at the very top, we're going to write const secure equals require crypto.js / SHA-256. And don't forget your semicolons. And so we're calling in the function to secure, which is coming from the library of crypto.js / SHA-256. And now we want to actually do something with this. So down here, we are going to write, we're going to create a function called calculate, which calculates the hash. Oh yeah, feel free to copy anything down if I'm going a little too fast. And let me know if I'm going too fast, if you want me to slow down. So right now we're creating a function called calculate. In this calculate function, we want to return any data and secure that data. So we're going to return, and we're going to say secure. That's just what we're going to leave it at for now. And inside of there, what do we want to secure? So we're going to take a string. So we're going to say our index plus our previous plus our time plus our data, which is going to be in a JSON format. JSON is a form of interpreting and like publishing your data. And so this is just going to be formed a little nicer. Feel free to copy that if it's a little too much. And then we're going to turn this to string into a string. So this is now our calculate function, which means any data that we add here, this will go into the function and it will secure it. Now we want to say here that our hash, this hash, the current hash, equals the calculated hash. So this dot calculate there. So what does all this mean? It could take some time to write this out, but we are referring to this library, crypto.js SHA-256, and now we're going to be using that to find the current hash. But what do we find the hash of? Well, we're finding the position, the time, the data, and the previous. And all of this is going to be secured into one string. It's going to be a long string like this over here. And in that string, that's all going to be calculated, and that's going to represent the current hash. So now the next thing we want to do is we want to actually build the chain. So this is how we hash data, but how can we actually create a chain around this? So we're going to go and create a new class called chain. And there we go. Yeah, feel free just to copy all this down for now. If you're not done yet. I'll give you guys a sec. All right, perfect. Okay, so we're going to be using the constructor props again. Once again, the constructor props is how we are able to initialize like a method. It's a method to initialize classes or data. So we're going to use a constructor prop, and we are going to say that this chain, this individual chain, will always initialize as the first block. The first block in a blockchain is called the genesis block. The genesis block is the very first thing. So the genesis block is the very first thing that you'll end up seeing on a chain. It's the very first thing, and it initializes everything that you see on the chain. So what will happen is you'll see your first one, which will have its individual hash, and then, for example, the second one. Let's say your second one, the only data in there is my name is Toby. That'll give us an output like this. And then, for example, the next one is my name is Tony. Let's say that's the second thing on the chain. That would give us an output like this. And as you can see, all of the hashes are the same length, but completely different in their identity, no matter how long the input is. So here we are going to now create a function called genesis. And we're going to say that always, the genesis block must always be a new hash. So we're saying this is a hash, a class of hash. So we're saying it must always be a new one of this. And its position will always be 0. Its date, let's give it a date of today. So 02, 05, 2022. And we'll say this is the genesis block with 0 as its position and 0 as its previous hash, because it's the very first thing, so it doesn't really have a previous hash. So this will be our genesis block. So we're always saying now that in the chain, it will always initialize with our genesis block. Now, we want to add 2 things. We want to add 2 things to our chain. A way to fetch the previous ones and a way to add the new ones. We want to fetch and we want to add. So let's create a function called fetch. In this fetch function, we want to return our chain. And in this chain, in this array of chains, we want to take the previous one. So we're going to say this chain length -1. So however long this chain is, however long that we're saying, for example, position 2, we're always going to say that length of 2 -1, that's the position that we're going to be using. So this will always fetch the one in the array, like that's the one right before. And this is a really good use of this prop and the length in order to identify which position in an array it actually is. That's all you need for the fetch function. Now we're going to add stuff. So if we have an input, how do we actually add that? So add, and we're going to call an input. And so we're going to be using this input for 3 things. First, we want the previous input to equal what we fetched. So we're saying this that we fetch and that hash. The second thing that we want to say is the input hash is the calculated. And the third thing that we want to say is that this chain will always push this data that is inputted. So a little overview on what we just wrote. So in this case, we have our chain, which always starts off with the genesis block. It'll always start off with that. We're saying our genesis block must be a new hash with this data. It has to start at the very first position with this date. It has to have this message, so it's the Genesis block, and its previous hash will always be 0 because it's the very, very first thing. Then we want to fetch data. So if we want to fetch any previous data, we just have to say we're taking this chain, this array of chains, and we're finding the previous one. And we're just identifying what that value is in the previous one. And finally, we're adding a new input. So given any input, we're saying the previous one must be fetched, that hash must be fetched. We're also saying that that hash must be the calculated hash, and the chain must push that. So that's all the code we're going to need for the first stage. So let's put it into action now. So yeah, so we are going to create a new chain. So any name ideas? Any coin name ideas? Any token name ideas? It's up to you guys. Orpheus it is. All right, perfect. So we're going to say let Orpheus equal new chain. So this is basically saying that we're going to that as our new chain, as this new class, we're just going to refer to this as Orpheus. So we're going to say Orpheus add. So we're adding, and we're using this thing right here. We're using our function add, and we're saying the input that we're adding must be a new hash 1 as the first index, 0, we're using the date today, and let's give it an amount of 50. And we have to add our semicolon, and that should be done. And so console.log, so console.log is how we put stuff in the terminal when we run it. So we're just saying we're going to stringify and publish our data. So with this code we have right here, you can copy this now. This should, when we type in node index.js in here, let me see if I can zoom in actually. Yeah. So at the bottom, node index.js, when you run that, that should output your new data. This will have your chain, which we have our chain, and this will have so our first block will be this right here. This represents our first block. It has a first index, it has a time, it has data, it has a previous hash, nothing, and it has a current hash. This is the current hash that developed. But the coolest part about this is that on the next one, so in the next one right here, it has its first index, it has a new amount, but its previous hash here is the same as this hash here. So our hash for the first block equals the previous on the second block. And I think that's really cool. And that's how they actually verify the chain. So this is essentially what blockchain is. It's just a series of blocks with data and hashes. So if you want to copy this code and then type, I'll put in here, node index.js in the shell, then you can output this data. And I think this is really cool, the way that the blockchain works. And for example, if I want to add another one, so let's say, I'll just add a new hash to, and I want to give it a new amount, like some random number. If I run this again, oh, my bad. If I run this again, oh, whoops. Oh, thank you so much. Whoops, that should, huh. Oh, yeah, that should work now. Yeah. Thank you. There we go. Oh, forgot to recall the function, my bad. Thank you for that, actually. Okay, yeah, so if you add a new thing, then yeah, you have your index, you have your new time, you have your new data, and you have your previous hash. This hash here will always equal this hash here. Your previous hash on the second index will always equal the actual hash on the first index. And I think that, yeah, that's the epitome of what blockchain actually is. So this is all you're going to need for the first stage. If you want to copy this down, now is the perfect time to do so. Yeah, and I'll just give you guys a second to do that. So yeah, this is done. Oh, how do we mine? That's the second stage. We're going to be going into mining difficulty and adding those zeros at the beginning. In case you don't know what that means, I'll get into that later. But yeah, actually mining the coins, that's the second stage, and using things like nonces, so your single use identifiers. So let's go right into the second stage. We're going to be using something called a nonce. So your nonce is a single use identifier. And this is a number added to your hash block that miners search for. So your nonce is independent, and it's used for every single individual block, and it's associated with that individual block, and it's never the same. So at the beginning right here, we're going to add something that says this nonce equals 0. We're initializing the nonce to equal 0 on the very first one. This is the very first thing that you want your nonce to be on your Genesis block. This will be the first thing that you'll see. Now, we want to go down here, and underneath the calculate function, we want to create a new function called mining difficulty. Also, sorry, right here in your calculate function, you're going to want to turn your nonces into a hash as well. So just in your calculate, if you want to recopy the calculate, or you want to add this in, you should always be adding your nonce into the stuff that you encrypt. So let's talk about mining. So your nonces are a single use identifier, and in this case here, we're going to be saying your mining difficulty. So mining as a function, and that difficulty. And we're going to create a for loop, a while loop for that. So while your array of difficulty is joined by zeros. So basically just saying when the amount of difficulty you have. So let's say you have the difficulty of 4, we're going to be joining 4 zeros with that. And that's if that does not equal your substring for the hash difficulty, then what do you want to do? So you want to increase the nonce, and you want to make sure that your hash is equal to what you calculated. Okay, so let's go over this. So when your array, so you have your array right here and its difficulty, we're saying +1 because arrays always start at 0. And we want to make sure that this is the actual array, the actual number that we're talking about. Arrays always start at 0, which means that it's always 1 behind. So the first one would be 0. So we're just adding 0 just to make sure it's the same number. And that's joined by zeros. When this amount is not equal to the amount of zeros at the front, we're going to increase this nonce. And we're going to then make sure that the calculated hash equals the hash. So I'll show you this right here. So at the beginning, you'll have, like, for example, let's say this is your, let's just say that is your hash, right? If that does not equal, let's say you had the same hash, but 2 zeros. This is saying that now we're going to add an extra 0 here, and we're going to increase the nonce. So we're going to make sure that the amount of zeros of the difficulty is always equal to the number of zeros at the beginning. The number of zeros at the beginning represent what mining actually it is. It represents how difficult it is to mine something. The more zeros, the more difficult, and therefore the more secure. So in our mining difficulty, we have this, and Now we're going to scroll down and we are going to, here we go. We're going to be adding a difficulty. So on the 30th line, or it might be different for you, but right in our constructor props for the chain class, we're going to give a difficulty. So this difficulty equals, let's use 2 for now, just something really quick. Now, how do we, now what does this actually mean? So I'm going to get into the idea of difficulty and validity. So I'm just going to go on full screen right here. Mining difficulty is the computing power necessary to verify something. This is why the blockchain is so hard to hack or even unhackable, is because you have to use computing power and you have to prove that you're human in order to use it. You can't, like, it's very difficult to use bots. And so this is just confirms that the user is a person. Something like this with a difficulty of 0. There's no zeros at the front, could take like 1 or 2 milliseconds to mine. But something with a difficulty of 5 could take upwards of 4 or 5 seconds, which in the long run is a very long time. It's a much more difficult process for computer processing. So what happens if someone chooses to attack the chain? What happens if someone chooses to attack the chain? So let's go down here and we are just going to, let's just say, let's just change some stuff up. So we're going to say that the Orpheus chain at its first position, we're just going to change the data. So let's just say amount is that big amount, right? And what if we just override this? This is probably one of the biggest threats in blockchain, overriding information on the chain, because then it's no longer immutable. So if I was to run this, for example, if you look at the first thing, the data here has changed. We're saying that now, when we change the data manually, we can just change the chain, and that's something we really want to avoid. So the next part, which uses nonces and uses the whole idea of hashing, is validity. And the whole idea of mining is that we can prevent things like this. So how do we implement this? So let's go, and we're going to scroll back up. Let's go right here. And so how do we, oh yeah, no worries. Good night. Yeah, so, okay, let's talk about validity. So how can we verify the chain? So there are 3 things that we need to verify. So we're going to create a function called validity. And in this validity function, we're going to say for when this initializer begins at 1, if I is less than the chain length, we increase it. It's as simple as that. When I is less than the chain length, we increase it until it reaches the chain length. And so let's say the chain length is 7, I just can keep on increasing until it's 7. So in this case, we're going to create 2 variables. We want the current and we want the previous. So the current one, we're going to say the constant of current equals this current chain in its I position. So we're going to say whatever this chain is, whatever it is at that current position, that's going to be what the current value represents. Then last, and we're going to say this represents the chain in the previous position. So given this information, given these things, there are 2 different ways that we can verify. We can say whether the current hash is equal to what was calculated. So if the current, we're using this variable, if current hash does not equal what was calculated, then if, gotta add parentheses, if the current hash does not equal what was currently calculated, then we return current hash is invalid, and therefore it will no longer work. Otherwise, we could say if current previous. So remember at the very beginning we called previous. We said what is the previous? So if we're saying what was currently in that position. If the previous does not equal the last hash, then return previous hash is invalid, and therefore it will not work. Otherwise, just return mined chain is valid. There we go, perfect. Oops. So this should be here instead, my bad. Yeah, okay, so now this is sort of detecting two things. First of all, we want to detect whether the chain is in the right hash and whether it has the right previous hash. And it's like, if you see here, if there's an unidentified overwrite, this will sort of identify and say, okay, rather than just completely eliminating this, we're just going to say, okay, it's not, we can't approve this, and therefore it won't go on the chain. And so that's what, so the blockchain, it's very quick in that sense. Rather than having to completely eliminate the hacker or eliminate someone trying to overwrite, you can just say, okay, nope, you're not going on the chain, all done. So with this code, let's see, we are going to test the validity. So we're going to say console log, and we're going to say Orpheus validity. And let me run this. At the top, it should say, yes, mined, chain is valid. And that's because, well, we didn't do anything to overwrite. We just said, okay, yeah, this is the chain, this is its validity, this is everything, therefore it must be valid. But what happens when we try to overwrite it? And so, okay, so if we try to overwrite it in this sense here, so we're saying on the chain in the first thing, we're just going to overwrite the data. So node index.js. And as you can see at the top, it says current hash is invalid because the hash that's right here on the first one is not what was actually supposed to be calculated. And so, yeah, it may look like the previous one is the same, but if this hash isn't what it's actually supposed to be as we initialize it at the very beginning, then okay, yeah, then it's not valid. And that's probably one of the biggest things when it comes to security, is that overwriting, it just completely eliminates that possibility. So this is it for, oh, I think I forgot to add mining. I'm sorry about that. Okay, yeah, so the final thing that I want to do is I want to add the whole idea of mining the actual data. So here, where'd that go? Oh, right, sorry. It's because I overrid it, my bad. Oh, sorry, that's in the next stage, my bad. I am very sorry about that. Okay, so mining difficulty will be in the next stage. I'm sorry about that, I mixed up the order. So feel free to copy this code down for now, and we'll be adding more stuff in terms of difficulty in the next stage. Feel free just to copy and paste the code. Yeah, so that's how, yeah, so in this case, this is just an example to identify it, but in the actual blockchain, like for example, in the Ethereum blockchain, if the hash is invalid or if the previous hash is not applicable, then yeah, then it's just removed, and it's actually go through. So rather than taking the entire process of like banning a hacker, for example, you can just make sure that the hacker can't actually add anything. So it's it reduces the risk of hacking and that sort of thing, in that sense, yeah. Just gonna quickly get some water. I'll be back in about in like a few seconds. Hey folks, all right, I'm back. Yeah, okay. So before we move on to stage 3, I just want to add or just fix a little few things. So in this case, I just use amount just as a small indicator. So what we're going to do is, here we go. We're just going to add a little more detail. So we're going to say that the sender, let's say Fiona Hacksworth. Yep. If this was a full peer-to-peer, can no one hear me? Oh. Okay, okay. Perfect. So yeah, Andrew, if you just want to leave the meter, come back, that might be good. So we're gonna say our sender was Fiona Hacksworth. Our recipient was, let's say centimeter Raj Agarwal, and it's quantity. Oh yeah, no worries. Quantity is 50. And what we want to do is we want to make sure that our input when mining is this difficulty. This is the thing I actually forgot to mention earlier in terms of mining. So up here, this is probably one of the most important things. I'm sorry for not mentioning this. I guess I just forgot. But yeah, so up here, I'll just zoom in. This, when you're inputting, it will mine at a certain difficulty. So at the very beginning, we mentioned something called mining difficulty and this function of mining at a certain difficulty. And so when you're inputting, this input should mine at whatever difficulty we identify in our initialization. So if we say 2, let's run this right now. Index.js. Perfect. It works. So if you look at this, your hash, the very first, the hash of the first block will have 2 zeros at the beginning, which meant it was pretty easy to mine. And that's just how difficult it was. So this is my favorite part. For example, let's say we increase the difficulty. Let's say 5. When you run this code, when you run it with a difficulty of 5, it takes much longer to mine. And it's right now still loading. It's using a lot of computing power in order to mine that. And that's the whole idea of mining, is that it takes computing power to mine at a certain difficulty, to actually mine this block. And this is why, like when you see these Bitcoin mining setups, they have like this large computing processors, because it's very difficult to mine when there's like the more zeros there are. I can't be exactly sure of how many there are with Ethereum or those kinds of things, but yeah, that's how it is. So as you can see, it's actually still mining. This is taking a while. Let's try something a little more lightweight. Let's try 4, which might be a bit easier for a computer and a little easier to show. So when it's loading, oh my God. What difficulty did you put it at, Ian? Oh, maybe it's because there's like 9 people on here. Is it happening for everyone else? Oh. If that is, I can just make a new one and then we can, oh yeah, okay. Maybe try reloading and see if it works. Because for example, now with the difficulty of 4, that took about, I think it was like 8 seconds to mine. And now there are 4 zeros at the beginning. Yeah, it should work with 4. With 5, it's pretty heavyweight. Yeah, so with a difficulty of 4, there are now 4 zeros at the beginning of the hash, and this is now all on chain. And for example, if I was to add let's add a new one and see what happens there. So let's add, I'm not gonna make the same mistake as last time. Add a new one, and we're gonna say this is the second, and with a quantity of that much, for example. When you run this, should take a few seconds. There we go, perfect. As you can see, this hash here equals the previous hash here, and they are the same with the zeros. And it's always the same amount of zeros at the beginning, which represents how difficult it is. I would advise just keeping it at 4 just for the sake of computing power. But it really comes to show how difficult it is when they increase the difficulty of these different blocks, and why the blockchain is actually so secure. Yeah, Andrew, I'll post the recording. Thank you for coming out. Okay, so now we're going to move on to stage 3. And this is my favorite stage, and this is the last one. Asymmetric ciphering. So what is asymmetric ciphering? You have your private keys and your public keys. So a user will encrypt, a user will encrypt something with a private key, their own private key, and they'll encrypt that information and it'll be sent to some sort of endpoint, some sort of central area. Now, when the other person receives that, they can only decrypt that with their public key. So there's a lot of standard ways right now where people just use the same key. Both people have the same key and they both use that to encrypt and decrypt. The only problem is it's hard when two people have the same, for example, password. Like if you want to get into your Google account, if two people have the same password to get it, like the same password, it actually gets it gets pretty difficult, and also it gets rid of the idea of security where you don't have your own password. And so the idea of asymmetric ciphering is very common on the blockchain, where someone encrypts information with private keys and they decrypt it in the end with public keys. So we're going to be implementing that using a Node.js library called Crypto. So at the very top, we're going to be adding some stuff. So const equals require crypto. Yeah, perfect. And we're just going to add 3 things here: public encrypt, private decrypt, and generate key pair sync. So in this library, from this one library, you can get a public key, you can get a private key, and you can generate this like a sync between the 2 keys, which allows it to encrypt and decrypt the same information. And this is really, really useful and really helpful. Yeah, feel free to copy that. It's a lot to type out. Yeah, so right here, well, this is the very bottom, sure. So at the very bottom, you want to add something and you want to say const. So you're creating a constant called private key and public key. And with this equals generate key pair sync. Now, there's a lot of different ways to encrypt and decrypt information. There are a lot of ways, but right now the way that I think is best for our case is called RSA. I was having actually an in-depth conversation with Ishan about this, talking about different types. But I think for our sake, RSA is the best. There are several different types. It's just one way to encrypt information and actually generate some sort of public key. There's so many different ways to cipher information, but I think this is the best way. So we're going to say RSA, and we're going to add information here. So first thing, how long do we want it to be? So we're going to say our modulus length, 2048. We're going to say our public key encoding. And this, I'm not really sure what they stand for, but this was recommended by Node.js, where you use this type, SPKI, and use this format, PEM. And for our private key encoding, we're going to be using type of PKCS8, and we're going to be using a format of PEM. And then boop and semicolon there. Yeah, so basically how this works is we know how long our modulus length has to be, 2048 characters. And in the public key encoding, it's going to be using this type, and in the private key encoding, it's going to be using this type, and they're all going to be formatted as PEM. Once again, I don't really remember the exact naming system for this, but yeah, that's how we're going to encrypt and decrypt, and we're going to generate these public and private keys. So we are going to say, let's just take a message for stuff. Const message equals Orpheus transaction, and that's just going to be our message, right? That's going to be what's being put on the chain through, for example, a smart contract or something we're going to put on the chain, right? So we're going to say const encrypted data. equals, so we're using what we used at the very beginning, public encrypt. So we're going to be using this function, public encrypt, and we're going to be bringing in our public key. So our public key is what one of the users has, and this is how they can encrypt and decrypt the information on their end. It's a personal key, something that they only have, and it's going to buffer from a message, and this message is what we identified right here. Next, const decrypted key, decrypted data, sorry, equals private decrypt with a private key and encrypted data. And we're gonna end it off. Okay, perfect. So, oh, whoops. Yeah, so with any message, this will encrypt the data with a public key and buffer that message from whatever the message is. And the decrypted data is going to allow us to use a private key to encrypt the data. So to use a private key on the encrypted data to privately decrypt it for your own personal use. So let's try here. So we're going to say orpheus add, and we're going to add our encrypted key as our encrypted data to string hex. And we are also going to say our decrypted is actually, we're not going to add our decrypted here. That's going to go in our validity. We're going to say that our public key equals public key. So I'll just get rid of this. When we run this, modulus length. Oh, oops. Thank you. Sorry. This should be a comma. I'm sorry about that. Please just update that. That should be a comma after modulus length. And so when you run node index.js, yes. Yeah, so this should be public key encoding type format, and then, oh. So right now, as you can see, the information is mining, and once that information mines, actually I'll add an update message here. So there we go, perfect. So what happens is on this block, on the very first block that we have our encrypted information right here, and we have our public key. And this also has our quantity. We have our previous hash, we have our current hash, and our nonce. And this is the fundamentals of exactly what needs to be going on to a blockchain. Yeah, thank you, Arash, for letting me know about that. Yeah, so this is everything that's going to be encrypted on the information, and all of that information is stored on this individual hash that we use as an indicator for position and for just the data in general. So the very last thing that's involved here is validity. So how do we actually verify this information with this with this key? So right here, we're just going to say, else if the decrypted does not equal our initial message, then return invalid data. And we're going to say that whatever we have as our decrypted must equal our decrypted data to string in a UTF-8 format. So we're saying that whatever our decrypted data is, that decrypted data put into a string in UTF-8 must equal the message. So basically, once we have a message, once that's encrypted, once it's encrypted and then decrypted, the final result must always equal the initial result. And so this is your new validity. This should verify anything that you need on the chain. Yeah. So now, let me just adjust that. Let's see. And the last thing we want to do is want to make sure the validity is inside the actual here. And we want to say that while it's mining, say mining. So we know that so we know it's actually mining, it's not actually an error. So at this point, the change should be done. If we run node index.js, it should say mining at the bottom. And as it's mining, this is just the process of it, adding zeros, and you have your index. You have this full list of everything that you need on the chain. All of this is stored in a single hash, and it's all encrypted and decrypted using public keys and private keys, using things like the crypto library. And it also has its individual nonce right here. It's single use identifier that it's searching for. Yeah. So voila, that's your own blockchain in 100 lines of code. Let's just go over what this really. Let's just go over what this actually means. Let's go through a bit of the code and how we can actually interpret this a little better. So right from the beginning, we have our we're importing SHA-256, which is a way to secure data. What data are we securing? Well, we're securing our index, our time, our data, our previous, our hash, and our nonce. Our hash is developed by returning all of this information and putting that into a string, which is then secured using the function by SHA-256. Then we're identifying the difficulty of this. So while we're saying, while the amount of difficulty of that amount of zeros must always equal the very few zeros at the beginning. Essentially, whatever's at the beginning must always equal a certain amount of zeros. And this is the substring from the very first zero to whatever value the difficulty is. And when it's not, that just increases the nonce, and therefore when that nonce increases, the hash must always equal what's calculated. Then you have your chain here, and your chain must initialize with your genesis block and with a certain difficulty. Your genesis block will always have this information here, and what happens is it always fetches the previous data. So in this case, when you fetch, you can return the array and what happened just before that. Then you can add new data. So if you want to add new data with whatever input you're adding, so whatever input you add, we can say that the previous must fetch using the fetch function to find the previous hash. We must take the current hash and have that make sure it's calculated. So we're using the calculate function in order to turn that hash, I can turn that information into a hash, and then we're going to mine it. So we're going to say that the difficulty must always be under the mining functions. Then we're saying that any information here must be pushed given a certain input, and that's being pushed onto the chain. Then to test for validity, we're adding three different things. We're saying that the current hash must always equal what is calculated using the SHA-256 function. We're saying that the previous hash must always equal what was said as the last hash. And finally, we're saying that the decrypted message at the very end must always equal the initial message from that transaction. And if not, then you can see here that the chain is valid. Everything's verified. If you try overriding, then it just becomes an invalid chain and doesn't actually get pushed to the mainnet. And that's how things in Ethereum work. In here, we're saying that we have our private and public keys. Our modulus length is 2048 characters. And with that, any public key encoding will follow this format, and any private key encoding will follow this format. Finally, we have our message, which is the actual message tied along to our transaction, and we have our encrypted data and our decrypted data. Our encrypted data uses a public key to encrypt it, and our decrypted data uses a private key to decrypt it. Then, for example, we can create a new chain. So Orpheus, we're calling it Orpheus. It's a token. This is how tokens work on chain. And this hash, what it does is it has a sender, a recipient, encryption, it has a public key, and it has a quantity. And these are the most common things that you'll find on a chain. And you can now use things like, and now you can determine the validity here, and you can sort of stringify this data. Well, yeah, so this is essentially what your own custom blockchain can look like. And this is the fundamentals of what makes blockchain so secure in the actual mainnet. If you want to add more things, you can just create a new one right here. And you can just like adjust all the information, adjust the index and all that stuff. But this is an entire blockchain built with all the features that you'll need, apart from peer-to-peer, which is a much different conversation, all in 100 lines of code. So yeah, we just tested it out. So as you can see, all the information comes up in a JSON formatter. This is also very good because you can turn this information into a, you can turn this information into, for example, a JSON API. And you can call that, and now you can create a public ledger for people to view on the web that they can only see with through verification. So we had four main things. We mine and hash blocks. We use proof of work. So proof of work is when you're using computing power, the work done by computing power, in order to verify and create those zeros at the beginning. We had fetching and adding transactions, so we can fetch previous ones and we can add stuff, like new stuff. And finally, chain validity. Yeah, so I'm going to quickly address the fundamental issue with custom blockchains. The problem with custom blockchains is that it takes away from the idea of decentralization. If everyone had their own custom blockchain, then those are just really tiny centralized communities. You don't really have something truly decentralized. So this workshop isn't necessarily like telling you to go out and build your own blockchain and make it something for people to use. It's more of a matter of understanding the capacity of existing blockchains and how you can use these to scale the future of web interfaces, to scale the future of digital interaction. With things like this, yes, there is that sense of decentralization through different senses of verification, but it's still very centralized on, for example, this REPL. And so for the sake of 100 lines, I think this was a very detailed understanding on how they work. But yeah, hopefully this gives you more insight on how you can use existing blockchains and sort of scale those up to the largest capacity. There are four main things, which I sort of spoke about at the beginning. This is really important because of distribution. So you're distributing all the data. This can all be published onto a mainnet, for example. There's ownership. So there is a standard, there was a recipient, there are hashes to confirm all of this. There is immutability. So we identified that with things like verification and validity. And finally, we have transparency. So in transparency, this like anything that you have here, this is transparent on the blockchain. And like, for example, you can view public ledgers for Ethereum, and this is all transparent. And it's sort of the idea of data should not be hidden. Data is yours, and the idea of privacy should be mainstream. So in order to scale this technology, you can use things like DAOs, so decentralized autonomous organizations that operate under the idea of power distribution, or equity tokens, smart contracts, or public ledgers. But yeah, thank you for building with me. I hope this was insightful, and I hope you got to learn about blockchains. Hopefully it worked for everyone on your individual device, or whether you just want to use it on the public REPL right here. I will be posting all the code shortly after, as well as a recording for this. And yeah, I'm really glad to see so many people coming out for the workshop. If you have any questions about anything with blockchain or anything in this sense, please ask them, and I'd be happy to answer them. Thank you. Thank you so much. There was a lot to cover, so hopefully I wasn't going a bit too fast. I think we finished right on time. How do I?